All right, so we're back here for part 2. And for this lesson here, we're going to talk about the confidence intervals for a difference in means. This is also a worksheet from the StatsMedic website. So confidence intervals, just as a reminder, the general form is we take the point estimate. So that would be the sample proportion or the sample mean. In this case, it would be the difference in the means. And then we add and subtract plus or minus the margin of error. And what that gives us is some interval of values where the middle here is the point estimate, but then we're going to add a certain amount and we're going to subtract a certain amount on either side. And that gives us our confidence interval where we think the true proportion, or in this case, the true mean, the true difference in means, is going to be between this value and this value. Now on your formula sheet, what we're going to do is we'll take the statistic, that's our point estimate, plus or minus. Now the margin of error is actually made up of two values. The first is the critical value, which is the z or the t. And in this case, since we're talking about means, it will be a t critical value. And then we multiply that by the standard error, the standard deviation of the statistic. But that's what we call the standard error. So the margin of error is we take the critical value times the standard error, which is SE. Okay, so the standard deviation of the statistic is the same thing as the standard error, because we probably don't know the population standard deviation. So we have to take the sample standard deviation, and that's what we call the standard error. Okay, so when we do a confidence interval, these steps, if you can remember the word panic, is we state the parameters. Okay, what is it that we're actually looking at, whether it's proportion or mean, the true proportion or the true mean. The assumptions that we make, those are the conditions, which are the random, the 10%, and the normal. We name the interval. Okay, and we have to specify whether it's a z interval or a t interval. We find the interval, we calculate it, and then we make our conclusion. So in this case, when we do check the assumptions, the conditions, all right, we've got the random, we've got the 10%, and when we do the normal, when we check the normal condition, if we're doing proportions, then we're doing n times p, and we're checking that that's greater than or equal to 10. Well, when we're talking about means, though, the normal condition is we need that the sample size is greater than or equal to 30. That's the central limit theorem. Or they tell us the population is normal, follows a normal distribution. Now, most times we're not going to deal with that situation. So we have to know that the sample size is greater than or equal to 30. Or if we graph it and there's no strong skew or outliers, we can use a normal approximation for that. All right, so the way the formula for the confidence interval itself is we take the statistic. Now in this case, it is a difference in means. So we will take the sample mean of the first population, and we will subtract the sample mean of the second population. That is our statistic, plus or minus. In this case, it is a t critical value for that. And then we multiply by the standard error, the standard deviation of the statistic. Now, on the sheet that we just did, we were using the population standard deviation. But most of the time, we don't know that. Well, that's why we're doing a confidence interval, is we're trying to estimate where the true mean is. So since we don't know the standard deviation, we do the sample standard deviation. So for the first population, that would be S sub 1 squared divided by the sample size of the first sample, N sub 1, plus the sample standard deviation of the second sample squared divided by the sample size of the second sample. Now, because we're using a t-critical value, we have to talk about the degrees of freedom. Now, degrees of freedom is n minus 1. But the thing is, we have two n values, and the sample sizes are not always the same. They don't have to be the same. So what we would do, if you're using the table, we would take a conservative value. We would take the smaller sample size. We would use the smaller sample size. And then subtract 1 for our degrees of freedom. Okay, so this is our formula that we're going to use. So let's take an example here. Check your understanding. So Mr. Wilcox's class performed an experiment to investigate whether drinking a caffeinated beverage would increase pulse rates. Well, we did this in class. 20 students in the class volunteered to take part in the experiment. All of the students measured their initial pulse rates at the beginning in beats per minute. Then Mr. Wilcox randomly assigned the students into two groups of 10. Each student in the first group drank 12 ounces of cola with caffeine. Each student in the second group drank 12 ounces of caffeine-free cola. And I think it's important to mention that they would have done this without knowing which one is which. All students then measured their pulse rates again. The table displays the change in the pulse rates for the students in both groups. So if you look at the table here, we've got the caffeine group and we have the no caffeine group, and the numbers represent the change in the pulse rates from the initial. They're taking the final pulse rate, subtracting the initial. So for positive values, which is what you see here for the caffeine group, for 8, that means that their pulse rate was 8 beats higher at the final pulse rate. After they had had the caffeine, it was 8 beats higher than the initial pulse rate. Now, if you see a 0, that means there was no change. And if you see negative values like here, that means this person's pulse rate actually decreased from the beginning to the end. And then over here, we have the mean change. So for the caffeine group, their mean change in pulse rate was positive 3.2. So their pulse rates went up. And for the no caffeine group, they also went up, but not by as much. So what we're going to do is construct and interpret a 95% confidence interval for the difference in true mean change in pulse rate for subjects like these who drink caffeine versus who drink no caffeine. So for a confidence interval, we're going to start with the parameters. So we're going to go through this panic here. These are our steps. So the parameter is, we're going to take the mean. Now this is, for parameter, we're talking about the actual population, the whole population. So what we're saying is that the difference in the means, the difference of the means, that represents the true difference in, and then basically we're going to copy this. It's the true difference in the true mean change in pulse rates for subjects like these who drink caffeine versus who drink no caffeine. It's important that we write down that we are doing this. Caffeine is our mean 1, minus no caffeine is our mean 2. So that's important that we're stating which way we're going here, because that will affect our values. All right, so that's the parameter. We're going to take the difference in the true means in the pulse rates. And what we're trying to figure out is, what is the true difference? We're trying to calculate that with our confidence interval. We're trying to estimate that. Okay, so parameters. The next is A, the assumptions. Now, the thing about this, we need to be careful. For the random assumption, for the random condition, the students were not chosen randomly. It says 20 students in the class, 20 students in the class, they volunteered to take part in the experiment. This is not a simple random sample like we would normally be using. However, the students were randomly assigned the treatments. Okay, so that is not the same as being randomly selected. However, the random condition is okay because they were randomly assigned. Because they were randomly assigned, though, we don't need the 10% condition. We don't need to check for independence. Okay, so in this case, you don't need to do the 10% rule. Now, for the normal condition, what we want to do is check the sample size. Now, both of these, n sub 1 and n sub 2, were both 10 people, which is not greater than or equal to 30. Those are less than 30, so we cannot use that. Now, we're not told that that the overall population is normal. We don't know that. So what we have to do is we have to take a look at the data and we have to check if there are strong skew, heavy skew, or if there are outliers. So this is where we would take the calculator now and we can go to stat. I've already typed in, so my list 1 is for the students who drank caffeine. My list 2 is those that did not. And I'm going to go up to stat plot here. Now I've turned both of them on, but just to show you that the first one, I'm going to do a box and whisker plot, and L1 is the list I'm using. And then for the second plot, I've also turned it on, but that is for L2. That's for the non-caffeine drinkers. You could do a dot plot as well if you wanted to. I'll do the box and whisker, so then I will do zoom 9. All right, and here is our L1. Notice that all the changes are positive, other than we had a couple of zeros. And here's L2, the non-caffeine drinkers. Some of their pulse rates actually went down. So there's a little bit different here. We have negatives and positives. But what I do notice is that there doesn't seem to be much of a skew. It's not heavily skewed. And there don't seem to be any outliers. Okay, now, to show that, obviously I see it on here and I can write down there's no heavy skew and there's no outliers, but I need to do a little bit better than that. Okay, so I'm going to draw a number line, and our negative values went as far as -2, 0, and then we went up to 8. I'll go ahead and number every 2 here. So if I'm doing this on the test, I do want to be accurate. So if I trace for the first one, so this is for the caffeine drinkers, we have 0, 1, 3.5, and then the third quartile is 5, and the maximum is 8. Okay, and I'll write down this is for caffeine. And then for no caffeine, we've got -2 for the minimum. The first quartile is -1. The median is 2.5. The third quartile is 4. And the maximum value is 5. So here's our box plot. And this is for no caffeine. All right, and again, we can say here, there is no heavy skew and no outliers. So we can use a normal approximation. All right, so those are the assumptions. That's good. Now, we need to name the test. This is a two-sample T interval. So two-sample T interval for means. In this case, this is mean 1 minus mean 2. Now, because we're doing a T interval, we need the degrees of freedom. If you use the calculator, it'll do all of that for you. But if we're trying to be conservative, both of the sample sizes are 10. So we would use, if we're using the table, so if we use the table, the degrees of freedom would be 9 for that. All right, so now what we need to do is to calculate the interval. Now we've got this formula here. So we're going to subtract the sample means. In this case, they tell us, the mean change is 3.2 and this is 2.0. Now something else we're going to need is the sample standard deviation. So I can go stat calc one variable statistics. The caffeine is list 1. So for list 1, the sample standard deviation is 2.6997. Now in this case, I'm going to say 2.7 for that. Or I could go 2.6998 if I want to be really accurate. Okay, so I'll put it up here. The standard deviation, the sample standard deviation is 2.6998. And then for the no caffeine drinkers, I'll go stat calc one variable statistics list 2. And that is 2.6247 sample standard deviation. Don't use the population standard deviation. We're going to use the sample, 2.6247. Okay, and I'm going to stop there for part 2.